All right, boys and girls, I hope you're having a good holiday. We're going to go over some of these problems together. I hope you've been doing them. Remember, they are due on the Monday you come back, so that's less than a week. And we're not accepting any lates for these either. So one thing I thought I would do is, if you've been working on them, that's great. I haven't received any questions, but any of the questions so far, maybe that's a good sign. But I thought we'd go through it and just to make sure that you understand completely what's expected for you to do. So remember, we only need to complete until page 10, so we don't need to complete it all. Okay. So on the first page, we've got copies of different things about solutions. What is a solution? Properties of solutions. Here, you'll see that there are some blanks. This doesn't mean that we just leave it blank. You were told that we need to put a definition in here. Okay? So it tells you a solution is a homogeneous mixture. Remember, we've gone through kind of the classification, taxonomy of matter many times, but if you want to remember, you know, we have all matter, right? And it breaks down into mixtures and pure substances. Okay. With our pure substances, we've got compounds and we've got elements. So that you can see elements. So this is just our raw kind of things we find on the periodic table, like carbon, for example, hydrogen, ding, ding, ding. Compounds, we have more than one thing bonded together. So we've got things like, you know, water, that kind of thing. Sugar. These things or compounds can either be ionic, like salt, or they can be molecular, like sugar, kind of thing. Okay? The other thing, for the mixture side, we've got homogeneous mixtures. Right? Things that are all the same all the way through. And then we've got things that are heterogeneous. They've got different, sorry, I need to push that in. They've got different phases that are clearly visible. So if you mix your good old oil and water together, you've got your heterogeneous mixture. They fall into two further categories, right? You had colloids. They're the ones that are not going to settle out, so you've got little droplets that are suspended within the solution as well. So something like milk is a good example of a colloid. There, if you look at it very closely, you've got little globules of fat that are suspended within the kind of milky substance. And the other kind you have is a suspension. Right, you should have this in your notes anyways. Your suspension, and that's something that will settle out on its own given enough time. So if you went to collect some river water, it would be very dirty and mucky and murky for a little while. But if you let it sit overnight, it should form into a very dirty layer at the bottom, which is very clear, and a clearer kind of water layer at the top. So that's an example of suspension. Homogeneous mixtures, these are our solutions. This is what we're studying about, homogeneous solutions. So you should be able to tell what is a solution. Solution is a homogeneous mixture. That's what we have right here. And it's saying, right, our solution has two parts, right? We've got the solute and the solvent. Okay, the solvent is the part that it does the dissolving. Okay, you need to write some sort of definition down. It does the dissolving. It's the bigger part. The part that's more will always be your solvent. Okay, so a lot of the cases we're looking at, water is our solvent. Right? We mix sugar and water together. We get water as your solvent, and sugar then becomes the solute, the thing that is dissolved. Okay. Okay, properties of the solution, they can be clear in that doesn't mean that light doesn't necessarily pass through it, although that's the case in many cases. It just means that we can't see little bits floating around inside. okay? There's no way that it can settle through when it stands. That's like a suspension, okay? It passes through filtering apparatus easily, right? There's nothing that's going to be stopped by the filter paper, that kind of thing. Electrolytes in solution, right? So these are the dissociated bits in the solution, right? So if we had salt, right, which would be our solute, right, it can break down into sodium ions and chlorine ions, okay? Those are electrolytes. Non-electrolytes are things that will not break down in solution. They won't break apart into constituent ions. So something like an oil, water, that kind of thing. Okay. So there's usually a change as well in the amount of energy that's involved when a solution is formed. We know about energy changes because these are read in changes in temperature. When we're talking about energy changes in chemistry, usually we're talking about changes in temperature. So we've got two cases here. We've got our endothermic and our exothermic. Endo means out, thermic means kind of heat. Endo means kind of in, exo means out, exit, that kind of thing. So an endothermic reaction it absorbs heat energy or thermal energy, and it would feel cold. Okay, an exothermic one releases heat energy, and if you were to touch it, it would feel hot. Okay. We did a nice example where we mixed, for endothermic, we had ammonium chloride in water. That one definitely felt endothermic. The temperature decreased. Remember, we saw that. Exothermic, if you're ever doing a dilution with acids, so we've got a really strong acid and we need to make it a little bit weaker, a little bit safer to use in a lab, and so we dilute it with some water. That is strongly exothermic, to the point where you really need to be careful. Okay. So, classifications of our homogeneous solutions. A saturated solution. Okay? So, solution is considered saturated. Solution is saturated when no more solute can dissolve in the solvent, and here's the big point, at a given temperature, right? Because temperature changes the solubility at a given temperature. Okay? Saturated solution represents an equilibrium, so that's the amount of dissociation and reassociation of ions. So the kind of the rate of dissociation and reassociation are similar. Okay. An unsaturated solution means that more solute can dissolve in a solvent at a given temperature. That's very important because that will change much, okay? Supersaturated, the word super means above, super, superior, means that more solute is dissolved in a solvent given temperature. So it's over its saturation point. Okay. So then we also we spent some time looking at all the different examples of different kinds of solutions that are out there. These are all kinds of things that you need to know. We tend to think of solutions mainly as being, we've got kind of water solvent, so a liquid, and a solid, something like sugar or salt, so a liquid solid solution together. But we can have different kinds. So solid, these, you might not think of them as solutions. These are things called alloys. Right? So they're two metals that are mixed together and they increase kind of the properties of it. Remember, the metal that's the bigger one will be the solvent, and the less one will be the solute. So an example here could be steel, right, where we mix carbon and iron together, carbon and iron. Solid liquid, this is just what we've been doing all along, so sugar, water is a good example. We're making a kind of juice, that's one. Okay, gas solid. This is, you can get something called camphor, which is from a tree, and sometimes they mix with nitrogen gas. That's a good example. Liquid, two liquids together. Vinegar is a good example. Vinegar is acetic acid plus water. Gas liquid, this is like oxygen that's dissolved in water. Gas is like our atmosphere, what we're breathing in right now. Okay, we should be able to talk about each of those and give examples of the different kinds of solutions. Okay, so at the bottom here we have the different factors that affect or, careful, affect, defect. Affect means influence. Okay, affect the amount that something can be dissolved into something else. Okay, one of the big ones we looked at was polarity of the molecules. How you determine that? Two things. You look at your electronegativity values. Electronegativity, and remember when you subtract them, the change, if you get a number between 0.5 and 1.7, that's considered polar. That's your magic number there. Okay. The other thing is that's not enough, because you can have bonds that are polar bonds, but the overall molecule might not be a polar molecule. So the other thing you need to look at is asymmetry. So what this means is that we have dipoles that won't cancel each other out, that they won't run in opposite directions. So if we look at the classic example of a polar molecule, we've got water, we've got the positive end running to the negative end, positive running to the negative end. If I tried to slide these two dipoles together, they would not cancel each other out. However, if I looked at something like carbon dioxide, which we're going to carbon dioxide, let's just say 1, 2, 3, 4, 5, 6, 7, 8, full octet. Okay, this is a linear one. It's going to go from positive to negative and positive to negative. And if I slid these over, they would line up on each other and cancel out. So this is a linear molecule that is symmetrical. So that means that the dipoles would cancel each other out, which means it's not polar. Okay? Okay, so we know that solutes dissolves in solvents that have similar degrees of polarity, okay, such that the positives and negatives can attract. Okay, this is what we keep saying again, like dissolves like. So polar solvents dissolve polar solutes, okay, and non-polar solvents dissolve polar salt. Non-polar solvents dissolve non-polar solutes. Okay, so just so we remember it. So if we have a non-polar solute, polar solute type. So we just need to get them all together, need to be lined up. So better don't worry about that chart. Let's just do some examples. So we've got different molecules here. We need to draw the Lewis structure. Okay. The Lewis structure, what does that tell us? It tells us about this kind of symmetry of the molecule. And then we'll be able to tell whether it's polar or non-polar. Right? We need to calculate the electronegativities, and then you need to decide whether it's soluble in water. Right? Water is our primary example of the polar. And carbon tetrachloride, any of these organic solvents, they are all non-polar. Okay? So carbon dioxide, okay, carbon's got four valence electrons. The one with the lowest electronegativity, put it in the center. And then let's bind it up. So oxygen has 6 valence electrons. Remember, to be happy, it needs 8, a full octet, except if it's helium, but helium is going to be fine by itself, so you don't need to worry about it. Hydrogen's the big example. It needs 2 to be happy. Everything else needs 8. So this carbon needs 4. So you know, 1, 2, 3, 4, 5, 6, 7, 8. Carbon has 8. This oxygen here has 1, 2, 3, 4. And then I'll put some lone pairs, 5, 6, 7, 8. This one, same thing, 5, 6, 7, 8. So this is a linear molecule. So if the shape itself being linear is going to tell you that it's non-polar, okay? If you calculated, you'd probably find that it might be 0.5 or something, so the bonds themselves might be slightly polar bonds, but the actual directions of the dipoles, right? So this is going to be positive to negative going this way. This is going to be positive to negative this way. If we line them up, they're going to, this will go over here. It's going to cancel out. So this one is going to be in carbon tetrachloride. Carbon tetrachloride. Okay, it's, remember, this is a 2 nonmetals together, so we need to use the rules. But tetra means 4. Okay, so what do we have? We have, this is an organic molecule. We haven't learned how to name these yet. I don't know if we'll have time to do that, but that's fine. So draw this. Your least electronegative goes in the middle. And it's going to look like this, oops, I've only got one. Okay, hydrogen needs 2, so that's 1, 2, that one has 2, that one has 2, that's fine. Carbon needs 4, carbon has 4, it needs 8, so that's 1, 2, 3, 4, 5, 6, 7, 8, that's fine. Chlorine, right, has 7 valence electrons, so it's going to share 7, yeah. It's going to share that one. This one, so if we look at these, all these bonds here are non-polar bonds, okay? And so the only polar bond is the carbon-chlorine bond. So it's more positive from the carbon going up to the chlorine. So that is going to make a slight pole. Right, remember we draw it, this one's going to be slightly positive, this end's going to be slightly negative. This one is going to be slightly polar, and so it should dissolve in water. It's going to be polar thanks to that chlorine. Okay, classic example of water. So looks like this. Hydrogen is 2, 1, 2, 3, 4, 5, 6, 7, 8. There we go. Water is this classic bent shape because of these lone pairs of electrons. It is absolutely polar, and so it dissolves in water. Water dissolves in water. NH3. Nitrogen has 5. There's a 3, 1, 2, 3, 4, 5, 6, and then a lone pair on the top, 7, 8. That's kind of going to push that down a bit. Because of that lone pair, it's going to make it polar, and it's going to dissolve in water. Calcium chloride. Okay, so calcium, this is hard because this one is going to be ionic, and you're going to see. So I'm going to draw the 2 valence electrons for calcium like this, and then chlorine has 1, 2, 3, 4, 5, 6, 7, and the other chlorine 1, 2, 3, 4, 5, 6, 7. This is going to move in here, and this one's going to move in here. It's going to give us calcium 2 plus and 2 Cl. Since it's gained an electron, it's going to be minus. This is ionic. Involves the giving and taking of electrons. And it will, because it's kind of polarized, it will dissolve in water. Okay. Salt we've done many times before. It's ionic, and we know it will dissolve in water. And iodine is, you already know iodine is going to be non-polar. It's got 7. It's like chlorine. It's got 7, 7. Because the electronegativities are going to be the same. Number one, it's going to be linear molecule, but the electronegativities are going to be the same. So once you subtract them, it's going to end up being 0. This will be non-polar. So this one is going to be in ClCl4. A little bit on our solubility curve. Number 1 says, at what temperature will 100 grams of water dissolve 60 grams of, ammonium chloride in a saturated solution? So we just go to our chart. So we want to know the temperature. So it's going to dissolve 60 grams, and if you want to be particular, we can get our water out. It looks like about 65 degrees Celsius. Okay. How much ammonium chloride can be dissolved in 100 grams of water at 80 degrees Celsius? So this one, just start here with our 80, and we're going to go up to our line, and go over. Ooh, that's again going to give us, I don't know what that, maybe 68. You can answer the other ones. Okay, done that before. How does temperature affect solubility? So for solids, right, as the temperature increases, solubility also increases. Okay, you can always keep throwing more sugar into water at higher temperatures. Okay, now that's different from the gases, though. With gases, it's the opposite. So as temperature decreases, solubility increases. And you can see that we've got some nice examples here. So We've got sulfur dioxide, which is a gas, and you can see that as the temperature here is increasing through time, the solubility is decreasing and kind of flattening out. And here we've got ammonia here, ammonia gas, and we can see that it's got a high solubility at 0 degrees, but as the temperature increases, it slowly decreases over time. So we've done lots of examples like this, so I'm going to let you do that yourself. Okay, a few things that we haven't done that you might want a little bit of help with. So, writing the equations for soluble ionic compounds. Okay, also be sure to count the moles of dissolved ions to make sure. Okay, so NaCl solid is going to make sodium ions. Of course, we need to state the state there. It's going to be aqueous plus chlorine ions, aqueous. Okay. This is aluminum acetate. It's acetate, so we've got aluminum, and the charge for aluminum 3+, aqueous plus acetate, which is C2H3O2. We need to be careful. We've got 3 of those, and that's going to be minus aqueous. Barium hydroxide, so barium Ba2+, aqueous plus 2OH minus aqueous, kind of like this. You could keep doing these examples on and on and on. Manganese, you could do this one with manganese 3 carbonate, so we just need to remember what this means. The 3 here is going to tell us the charge. Manganese is Mn, carbonate is CO3. Manganese 3 tells us we've got 3 of those. Carbonate's got a charge of -2, so that means we need 2 of these. Okay, so that's going to be solid, and that's going to give us 2 manganese 3+ aqueous plus carbonate, which is so we got 3CO3 2 minus aqueous, like this. Okay, and you could go through, and I'm sure you could do all of these examples, but that's kind of what you're doing with those. Then what we looked at before, we had our solubility rules. You've got all the different solubility rules here. So you know that anything in group 1 is going to be soluble, no exceptions. Everything's good. Ammonium is always soluble. Nitrate, always soluble. Acetate, always soluble. Hydrogen carbonate, always soluble. Chlorate, always soluble. Any of the halides, there's a few rules. So except for, the halides, most of the time we see them is with group 1, right? So that's okay, but if there are any of these ones, okay? The sulfates mostly okay, except when you've got a couple there from group 2, calcium and barium. But again, a lot of things with silver or lead are not necessarily soluble, unless they're with one of these ones that are always soluble here. Carbonates are generally insoluble, okay, except if you have any of them that form with a group 1, okay, because those ones are always soluble. Chromates are generally insoluble. Phosphates, okay, except same sort of rules for those. Sulfides, same sort of rules, and hydroxide, same sort of rules as well. Okay. So if we go down to the bottom, it says Are the following compounds soluble S or insoluble I? So I don't even need to think about sodium chloride. I've seen it dissolve many times throughout my life in water. Okay? But why would that be? Well, it's got a halide, which is generally, chlorine's a halide, generally soluble, and it's got a group 1. Okay, so what's this one? This is iron chlorate. Chlorate, if we go back up here, it says chlorates, no exceptions, are soluble, so soluble. Calcium sulfate. Okay, sulfates, generally soluble, except when we've got calcium, it's insoluble. Next one, ammonium hydroxide. Ammoniums are always soluble, so we're fine. Barium, next one is barium phosphate. Phosphates are generally insoluble, except when they're with group 1s or ammonium. Barium is group 2, so it's insoluble. Next one, we've got magnesium chromate. Chromates are generally insoluble. Okay. Carbonates are generally insoluble too, for this next one. And you could keep going through all these different examples. Okay, there's lots of them there. Just look at your chart. Again, unfortunately, you're going to need to memorize them because you need to know which ones are soluble and insoluble so that when we start making them in our solutions, then you can write these equations down. Okay. So, before we left, we were looking at some double replacement reactions with everything. Okay. Double replacement reactions involve aqueous solutions and they make a solid or a precipitate reaction, and they can be represented in 3 different ways. So your molecular equation, we can think of this as just the regular equation that we've been using all year. Okay, it shows all species involved in the reaction in their molecular states. Okay. This one, complete ionic equation, shows all ions in the reaction. Remember, these things, you know, all of them need to be balanced. Okay, so that one needs to be balanced. This one, you're going to make sure it's balanced too. Net ionic equation, it cancels out all of the spectator ions. And uses the ions involved in making the precipitate. Okay. And spectator ions are just the ions. Remember, they're like spectators at a sporting event. They don't really do anything. They're the ones that are not involved in the precipitate reaction. Okay, so it's giving you an example here. So what do we have here? We've got cobalt-2 chloride, and it's in solution, it's aqueous. That's nice. So that tells us that this thing is soluble because it's aqueous. And what do we have? We've got sodium sulfide, aqueous. Oops, sulfide's generally not soluble, remember, but since it's with a group 1. So these are double reactions, so that's always the switcheroo. So this is going to, let's go. So we've got cobalt, and it's going to join up with sulfur. Careful, this is not copper. I sometimes make this mistake too. This is cobalt, CO. Sulfur's got a charge of 2 minus, cobalt there's got a charge of 2 plus, so that's the case. I'm not going to put the state of matter here. I'm going to consider that after I'm finished. And then the next part I've got sodium chloride. Okay. So sulfides, as we remember from our chart, sulfides are generally not soluble except when they're with group 1 ions or with ammonium. So this is going to form your solid precipitate, and then this is aqueous. Okay, so what do we need to do? We need to balance it out. Cobalt balance, Cl2, Cl1. 2 there. And sodium 2, sulfur 1, sulfur 1. Okay, that's balanced out. So complete, i.e. complete ionic equation. So we're going to break this apart to all of its pieces. So cobalt 2 plus aqueous plus chlorine minus aqueous, but don't forget we have 2 of them there, so we're going to put 2 here. Okay, plus 2 sodium aqueous plus it's going to give us So this is our solid, so we're just going to write it together. 2Na plus aqueous plus 2Cl minus aqueous. Okay, so the net ionic equation, what do we need to do? We need to make sure we cancel all of this stuff out. So we're going to cancel it out. Cobalt, but cobalt's involved, so I'm not going to cancel that out. 2 chlorine, that's going to cancel. 2Na, da da da. So our complete is cobalt 2 plus. Cobalt 2 plus. Okay. There, and you can make a list of all the spectator ions as well. Okay. Let's do 1 or 2 more. So what do we have here? We've got calcium chloride plus, that's pretty similar to the last one we just, well, let's do it. Okay, it's very similar, but let's do it anyways. Calcium chloride plus sodium sulfide. So our complete, so first we need to finish the molecular equation. So if we finish the molecular equation, we get calcium sulfide. Calcium's 2 plus, sulfur's 2 minus. We'll just leave it like that. We'll consider whether it's soluble after we're finished. Plus calcium sulfide plus sodium chloride. Sodium's +1, chlorine is -1. Okay, we know that sodium chloride always dissolves because it has a group 1 metal mixed with a halide. Those always dissolve. Sulfur, a sulfide, as we remember, are generally insoluble, with the only exception being when it's combined with a group 1 metal or ammonium. Calcium is a group 2 metal, so it's not going to be soluble. That's going to form an S and make a solid precipitate. The next step we need to do is make sure that this is balanced. So we got 1 calcium, chlorine 2. It means we need to have 2 chlorine there. We've got 2 sodium there. Now we've got 2 sodium there. 1 sulfide. That's fine. Next step, you need to write out your complete ionic equation. So you need to break it apart and write down all the different ions. Okay, so calcium Ca aqueous 2 plus 2 chlorine minus aqueous plus 2 Na plus aqueous plus S2 minus aqueous makes Ca2, no, my mistake. So that's a solid precipitate, so we just write it all together. Calcium sulfide, and then plus 2 sulfur aqueous plus 2 chlorine minus aqueous. Okay? Your net ionic equation, you're going to cancel everything out. So if it's the same on both sides, we're not going to worry about it. So calcium is going to be involved, so we can write it here. So calcium aqueous 2 plus chlorine. It's going to be on both sides, not involved, so we don't need to worry about it. Sodium is on both sides, not involved, so we don't have to worry. Write it down. Sulfur, we need to write it. 2 minus aqueous makes calcium sulfide. Now, it should be balanced too at the end. If not, you've done something wrong. All right, I'm just going to do one more example and then leave you with that. And you should have enough knowledge to do the rest of it by yourself. If you have any problems, let me know, and I can do a few more questions for you. So what do we have here? For number 2, we've got sodium bromide with silver nitrate. So again, it's a double replacement reaction. So that's going to give us sodium nitrate. Sodium's got a charge of +1, nitrate's got a charge of -1, so that's fine. Again, I'm going to leave the state of matter until I've considered everything to the end. Then I've got silver bromide at the end. Okay, group 1s are generally soluble, and I believe nitrates are always soluble too. So this is going to be aqueous, it's going to dissolve. Bromine is a halogen, except it's got silver there with it, so that's not going to dissolve. So that's going to be a solid precipitate. Silver usually doesn't dissolve anything, much like lead and mercury as well. Okay, the next thing we just need to make sure is everything is balanced out. So we've got 1 sodium, 1 bromine, 1 silver, 1 nitrate, 1 nitrate. That's balanced out nicely, don't need to do any work. Complete ionic equation. Na plus aqueous plus Br minus minus aqueous plus Ag plus aqueous plus NO3 minus aqueous gives us silver bromide plus Na plus NO3 minus. Okay, now you're just going to cancel everything out. And you should be left with Ag plus aqueous plus Br minus aqueous gives you silver bromide solid. Okay, that's about all that I'm going to do. You only need to complete to the end of page 10. You've had 2 weeks. Remember that this needs to be handed in or it is a 0. And since I've done most of the work for you, as long as you're paying attention, there should be no problem or anything. Okay? Enjoy the rest of your holiday.